Well, hello and welcome to my first session on linear differential equations. Now, this session is going to cover, I would say, almost all of linear differential equation. And it's really nice that I have compiled it into one video. Watch this and you're going to master the linear differential equations. So before I even start talking about linear differential equations, it's essentially more important to know what it is. Now firstly, differential equations are something of the form, a function of, I would say derivatives. So let's say x to the x's nth derivative, x's n minus 1th derivative, x derivative, x itself, and probably t is equal to something, or well, let's say just it's equal to 0. Now, first of all, you'll find this very confusing. Like, what is this stuff? I will just write it in some nicer fonts, for example, in a few times. So, let me give you some examples of differential equations. You must be already knowing what a differential equation is. So, one of the examples is y double dash plus 3y dash plus 2y is equal to 0. Solve for y. You are given with y dash plus 3y y double dash plus 3 times y dash squared is equal to 3t. Solve for y. So all these kind of equations which involve derivatives of the function itself, or the independent variable, which in this case is t right here, are called differential equations. Now, when we are talking about linear differential equations, it's important for us to understand that we're talking about a class of differential equations which satisfy a very nice property. Now, what is that property all about? So, let me just write a very simple differential equation. Y dash plus y double dash plus 3y dash plus 2y is equal to 0. What I can even write this as d squared over dx squared. Let me use y for the dependent variable and x for the independent variable. Where was I? So y double dash can be written as d squared over dx squared times operating, because this is sort of operating on a function yx, plus 3 times y dash can be written as d over dx, which is an operator operating over yx, plus 2yx. Now what I can do is, certainly enough, this is not a kind of thing where you can just factor out yx, but I would do that first. Let us see what happens. Then what we are left with after factoring out y is d squared over dx squared plus 3d over dx plus 2, this entire huge thing, multiplying on the function y is equal to 0. Now what I say is this itself is an operator. Now what is an operator? An operator is something that operates on something. So for example, d over dx is an operator, and it operates on function x, which produces 1. So this is the operator, this is the operand, let's say substrate, and this is the result. So this is itself is an operator. What we usually denote operators by is L and the independent variable, that is, which is x. So what we are saying is Lx, this entire thing we equated to Lx of y is equal to 0. An even simpler way of writing it is Ly equals 0. Some textbooks use this, I will use this one. Now what happens as we moving forward, it's important for us to go through how to use these operators, because you need to be handy with these things. If you're not handy with these things, then it poses some sort of difficulty. So I would first do some practice with these operators. So let me just do something. D squared over dx squared plus 2d over dx plus 1 operating on the function x squared. Now, d squared over dx squared of x squared is equal to what? D over dx of x squared is equal to what? And 1 times x squared is equal to what? We would run backwards. So 1 times x squared is equal to x squared. The derivative, we are differentiating x squared, so the derivative of x squared is 2x. Now this square literally means that we are just operating with the same operator once again. So this is equal to d over dx, 2x, and is equal to 2. So now we just add all of these up, and what we get is x squared plus 2x plus 2. Simple enough, right? We can also do some more. Let me just say 1 over x squared d squared over dx squared times 1 over x squared times d squared over dx squared plus 3 times d over dx plus 5 times d cubed dx cubed. All this monstrosity operating on a single function, that is e to the x. Now, one of the things that we know about e to the x is the derivative of e to the x is e to the x itself. So no matter how many times we differentiate it, the result at the end of the day is e to the x. So this can be written as 1 over x squared times d squared over dx squared operating on e to the x plus 3 times d over dx operating on e to the x plus 5 times d cubed over dx cubed operating on ex. Now all of these are equal to e to the x, e to the x, and e to the x. So this can be written as e to the x times 1 over x squared plus 3 plus 5. This is the answer. Okay? So I assume that we have got some sort of practice. I would encourage you to go to textbooks, and we would even, most of the things, to make things handy in differential equations, we generally use this operator notation because that's really simple to use, and I like it. The operator notation is right to concise up the equation. Sometimes the equations can be ugly, but if you write it in a compact form using these differential operators, I certainly like it. It makes things easier. Now, what are linear differential equations? There's basically a sort of differential equations which are well behaved, I would say. So well behaved. Now, how much well behaved, we should have a quantity for that. So let the operator be L, and let it be operating on a function A. Alpha is a constant, times any function, let's say y1, plus beta, where beta is any function, any real number, a constant, or not necessarily a real number, any number. So alpha and beta are any number, any numbers, and when we operate on this function as on a whole using this operator L, if we get alpha times L of y1 plus beta times L of y2, that means that L is linear. Difficult at the first time? Let's do some practice. Just get a feel for it. What I'm basically saying is a linear combination of two functions. A linear combination of two functions is a constant multiplied by the first function plus a constant multiplied by the second function, and you add them up. An operator, the operator that we're talking about, can be any operator. It is linear if and only if it satisfies the following property. Now we would check a few. I'll just keep the definition here so that it's easy for us to come back to it. So I'll just keep it here. I will just solve the problems here. So let us just determine whether some of them are linear, some of them are not. So here is our first example. Y third derivative plus 1 over x squared second derivative is equal to 0. Simple question, right? So the operator in this case, when we are having this variable x, because we're not having any sort of partial differential equations, this must be the independent variable, okay? It doesn't matter where it came from. What does matter is where it goes, okay? Now, alpha y1 plus beta y2. We're gonna apply this to this. We first find out what is the linear operator. What is the operator that's operating on it? That's the first thing that we are gonna do in the beginning. So let me just start it. Let me just start the problem. Let me just pause the video once, I guess.